Great. So I'd like to start by thanking the organisers very much for giving me the opportunity to present this work today. And the work that I'm going to present to you is some tools that I and others developed in Elspeth Garman's group to help you identify specific radiation damage artifacts in your protein crystal structures. So just for some context, when we collect a diffraction data set from a protein crystal, in fact, only a tiny fraction of the X-rays actually contribute to our diffraction pattern. So as an example, if we were to put a protein crystal of 100 micrometer thickness in an X-ray beam of wavelength 1 angstrom, 98% of the X-rays would pass straight through the crystal and not interact with it. And just 0.2% of the X-rays would be elastically scattered by that crystal to generate our diffraction pattern. And the remaining 1.8% of the X-rays are inelastically scattered by the crystal. And inelastic scattering means that those X-rays deposit some or all of their energy in the crystal. And the deposition of this energy causes damage. So radiation damage can be broadly divided into two types, global and specific. And global radiation damage affects the crystal lattice. So this manifests in your data as changes in reflection intensities, and in particular, you see this characteristic loss of high resolution reflections as you collect more data, and other effects include unit cell expansion and increased mosaicity. The second type of radiation damage is specific radiation damage, and this affects the molecules in the individual asymmetric unit copies. So specific radiation damage causes both structural disordering and also chemical changes. And these chemical changes have been observed to occur in a reproducible order with increasing dose. So for protein crystals at cryo-temperatures, with increasing dose, first your any metal ions and redox-sensitive cofactors are reduced, then disulfide bonds are reduced, glutamate and aspartate residues are decarboxylated, and the methyl thiol group is cleaved from methionine residues. And it can be very difficult to distinguish specific radiation damage artifacts from structural mobility. So for example, without any additional information, if we were to look at this glutamate residue here, it would be very difficult to tell whether the lack of electron density around this side chain is because this residue adopts multiple different conformations throughout the crystal, or because the carboxyl group has been cleaved off due to radiation damage. And what makes this problem worse is that specific damage affects onset before global radiation damage. So the experimental dose limit is a measure of global radiation damage. So it was calculated as the dose at which the total sum reflection intensities from ferritin crystals was measured to decrease by 30%. So the the experimental dose limit is 30 megagrays, shown here in red. And on the left here, I've plotted the approximate doses at which some of the specific radiation damage artifacts I mentioned a couple of slides ago onset. So you can see that these dose values are much lower than the experimental dose limit. So it's perfectly possible to collect a data set that shows no sign of global radiation damage at all, but actually still contains specific radiation damage artifacts that could lead you to draw incorrect conclusions from your structure. So what we wanted to do was to develop a range of tools to help users to identify specific radiation damage artifacts in their structures. And all of the metrics that I'm going to introduce to you today, they're all B factor. They're all based on atomic isotropic B factor values. So if you look at a PDB file of a crystal structure, you'll see that every atom has an associated atomic isotropic B factor value. And this value just tells you how much the position of that atom varies throughout the crystal. And all of the specific radiation damage artifacts that I introduced a few slides ago, they all cause the affected atoms to move, and so therefore they cause an increase in B factor value. But there are lots of other variables that also affect B factor values, and one of the main ones is structural mobility. So if we just look at B factor values alone, it's not possible to tell whether the atom in question, if it has a high B factor value, is mobile or whether it's been damaged. But luckily for us, the structural mobility of an atom is strongly correlated with its packing density. And the packing density is defined as the number of atoms in its local environment. So by correcting B factor values for packing density, we're able to remove a lot of the effects of mobility from B factor values, and the resultant values allow us to detect specific radiation damage artifacts. So a few years ago now, the Garman group developed the BDamage metric, and as I just explained, BDamage is B factor corrected for packing density. So to define this more formally, the BDamage value of an atom J is calculated as the ratio of its B factor value to the average B factor value of atoms identified as being in a similar packing density environment. So using BDamage values, we're able to identify potential specific sites of specific radiation damage within an individual crystal structure. However, there are a couple of drawbacks to BDamage. So firstly, it's a per atom metric, and from a per atom metric, it's quite difficult to get a sense of the overall amount of damage that a crystal structure that a structure has suffered. And secondly, BDamage values can't be fairly compared between different structures. And this is a result of the way it's calculated. Okay. Perfect. Brief interlude. Okay, so BDamage, when you calculate the BDamage value, you are comparing the B factor values of the atoms in a structure to one another. So therefore, even a structure that contains no damage at all is going to have both high and low BDamage values. And it's up to the user to compare the identities of the atoms with high BDamage values in a structure, compare those to known sites of damage to see if you think that those atoms that have high BDamage values are damaged. So for example, if your structure contained a disulfide bond and the sulfur atoms both had very high BDamage values, that would be a strong indicator that that disulfide bond had been reduced. So anyway, to complement BDamage, we also wanted to develop a per residue metric, a per structure metric that can be fairly compared between different structures. So the metric we came up to do this is BNet. So to calculate BNet, we look at the BDamage values of the oxygen side chain atoms of aspartate and glutamate residues, because these are known sites of specific radiation damage. So in the plot on the right here, I've plotted the BDamage values of these side chain oxygen atoms for a undamaged structure in blue and a damaged structure in orange. And this black line here is the median BDamage value of all atoms in the structure. So what you can see is that when a structure is damaged, the BDamage values of these oxygen atoms shift relative to the median BDamage value of all atoms in the structure. So to calculate BNet, we simply calculate the area under the distribution on the right-hand side of this median, and also the area under the distribution to the left-hand side, and then BNet is just the area of these two ratios. So you can see that when a structure is damaged, the area on the right-hand side increases relative to the area on the left-hand side, and so BNet goes up. So in the interests of time, I'm not going to go through all of these, but there are a few requirements for calculating BNet for your structure. And the most important of these is that because we are looking at the BDamage values of aspartate and glutamate oxygens, it is restricted to protein structures only. And secondly, we've only validated the metric currently on cryo-temperature data. So it's not suitable for room temperature data. So to validate BNet, we've calculated BNet values for several series of structures in the protein data bank that we know are damaged. So in each of these series of structures, the crystallographer has collected successive data sets from the same crystal or group of crystals, so they therefore know that the structures at the end of these series contain are more damaged than the structures at the beginning. So we calculated BNet values for these structures and plotted them versus dose. And what you can see is that there's an approximately linear relationship between BNet and dose. And moreover, that the gradients and y-intercepts of the lines of best fit plotted for these data sets are fairly similar. They're not identical, and there are a few reasons for that. The main ones being that there are quite a lot of errors associated with dose calculations, and also our correction for packing density to remove the effects of mobility. It does a good job, but it's not perfect. So we haven't fully removed the effects of mobility from BDamage and so BNet values. So anyway, nevertheless, given these errors, the gradients and y-intercepts of these lines of best fit are pretty similar. So we were happy that we could compare BNet values between different structures. So following on from that, we calculated BNet values for just under 94,000 cryo-temperature protein crystal structures in the PDB redo data bank. And what we wanted to do was check that BNet is reflective of the extent of radiation damage suffered by a structure and isn't correlated with other variables that are not related to radiation damage but might affect its value. So I've shown 8 of these here, and I've calculated the correlation coefficient between BNet and these variables. And if we take as a rough rule of thumb that a correlation coefficient of between negative 0.2 and positive 0.2 means there's no correlation between the variables, we can see that 5 of these variables, there's no correlation between BNet. However, there is a substantial correlation between BNet and resolution and R factor. And if we think about it, this is not surprising. For lower resolution structures, the electron density maps are more blurry, and therefore it's harder to distinguish the extra blurriness that decarboxylation of glutamate and aspartate side chains causes. So we wanted to develop a metric that could be fairly compared between structures of different resolution. So to do this, we made BNet percentile. So for BNet percentile, we group structures of similar resolution into the same bin, and then we compare the BNet values of the structures in each bin, and then assign the percentile rank to each structure. So that means that a structure with BNet percentile of 100 has the highest BNet value of all of the structures in its resolution bin. And a structure with BNet percentile of 50 would have the median BNet value of all structures in that bin, and so on. So if we look at the correlation coefficients between BNet percentile and these 8 variables, you can see that none of them, the BNet percentile isn't correlated with any of these variables. So here I've shown, so what I wanted to show here was radiation damage artifacts in 6 of the structures in our data set of 94,000 that have the highest BNet and BNet percentile values. So you can see that in all of these structures show clear signs of specific radiation damage. In their electron density maps, you see these characteristic negative electron density peaks around aspartate and glutamate side chains, and also around our sulfide bonds. What I'd like to focus on is that if you look at the metrics that we often look at to assess the quality of structures in the protein data bank, a lot of these structures have good to excellent values for these metrics. So in many cases, these metrics aren't picking up the specific radiation damage. So BNet and BNet percentile can potentially help you if specific radiation damage artifacts are something that you're worried about when you're selecting a protein structure from the protein data bank, for example, for protein engineering studies or molecular dynamics. BNet and BNet percentile can help you to check that these structures don't contain specific radiation damage artifacts. So to finish, I'd like to briefly discuss what can you do to avoid and detect radiation damage during data collection. So as several people have mentioned in the talks before, during your data collection, you can calculate the dose that's being absorbed by your crystal using the Garman group software RABDAM 3D. That's available on the Garman group GitHub page, and also, as was mentioned in the last talk, is online at Beamline 04. And also, as Ralph also said, talk to your Beamline scientist to check that your data collection setup is sensible. During refinement, we've made a program called RABDAM that allows you to calculate the metrics I've introduced to you during this talk for your structure. And it's currently available on the command line. So any terminal with CCP4 tools enabled, you simply run it by typing RABDAM -F and then either PDB accession code or the path to PDB or MMSIF file. And again, the software is available on the Garman group GitHub page, as well as details, more details of how to run it. So if you do find that you have specific radiation damage artifacts in your dataset, unfortunately, the only way to get rid of them is to go back and reprocess your data with fewer images. But here I'd just like to emphasize the difference. Oh, those numbers are the wrong way around. Oops. Emphasize that by removing only a few images, you can actually get dramatic improvements in your electron density maps. So this should be 588 and this should be 555. So you can see that by removing under 5% of your images at the end of your data set, you get a substantial improvement in the quality of the electron density around this cofactor. And then lastly, as I mentioned before, you can also run our software RABDAM to calculate BDamage, BNet percentile metrics for structures that have been deposited in the PDB. So with that, I'd like to thank my supervisor, Elspeth Garman, the Garman group members who developed the metrics that I presented to you today. So Marcus Gerstel developed the BDamage metric, and Johnny and Tom wrote the initial version of the RABDAM software. And I'd like to thank you very much for your attention. Thank you.
Thank you very much, Kathryn, for that very interesting talk. Any questions?
Hello, Jean Bricogne. Clemens von Rijn will be talking tomorrow about a way of catching in the data themselves indications of radiation damage. So it's a superset of what you did at the very end, using only the initial data to get better density. But if you compare the initial and the final data, you get a map of where electron density has disappeared because of radiation damage. That's been around for years as a feature of AutoProc, combined with Buster. Thanks.
Hello, Harry from Cardiff University. When you looked at the BNet values for the different structures from the PDB redo, did you find any relationship between the resolution ranges and the radiation damage found at those resolution ranges?
So we found that for structures with lower resolution, that the BNet values tended to be lower.
Okay, thanks.
Hi, Mike Huff from Diamond Light Source. You mentioned that the analysis isn't quite so valid at room temperature compared to cryogenic temperature. How high in temperature can you go and still be able to apply those methods?
So at the moment, we've only looked up to 120K. I've only compared cryo temperatures relative to room temperatures just because of there's not a huge amount of data between those. But yes, it doesn't work particularly well at room temperature, which I would guess is because of the larger effect of dose rate at room temperature as compared to at cryo temperatures.
I have a question. Would it be feasible to add the BNet values into the PDB for every structure, or would that be too complicated?
If the PDB would like them, then yes, it would be feasible.
Okay.
Hi, Samuel Foster from University of Leicester. I was wondering if you saw any correlation on the PDB with proteins that contain metal cofactors and the BNet values.
So we can't use BDamage values to look at damage to metal ions or cofactors simply because they often have sub-1 occupancy, and that obviously has an impact upon the B factor values. So we did initially try and calculate BDamage values for metal ions, and it didn't work at all. So we've, for that reason, restricted our analysis to proteins.
Peter Moody, the negative density you show on the side chains, this is from PDB redo structures from the database, from the PDB and data. Right, so, I mean, surely all that does is shows that the description of the structure is wrong, that the model is wrong in that either the temperature factor is wrong or the occupancy should have been adjusted. Negative density is a reflection of a poor model at that point rather than anything else. I mean, obviously, when you've lost them, it shows decarboxylation or whatever. But were you selective in choosing your examples there? Because
No.
I would have thought some depositors would have adjusted this in their structures.
So the analysis was run on structures that either have aspartate and glutamate residues that have 100% occupancy. So alternate conformers, they can have sub-1 occupancy, but it must sum to 1. So yes, in that respect, we were selective. But realistically, I would argue it's rare for people to do occupancy refinement of aspartate and glutamate residues to take account of radiation damage.
Well, they might inspect them, their maps.
Sorry to hog the microphone. This just shows the problem with comparing models with merged data. If you had the unmerged data available, you would be able to track that loss of occupancy as a result of local radiation damage.
Really making it work.
So, James Noble or Charles River. So, if someone has gone through and deposited their structure and seen there's negative density around their aspartates and therefore removed them, that will, of course, make this metric not work at all.
Yes, but the point of the metric is to help you identify these artifacts in your structures. So if you've accounted for them, then no, it won't pick them up. But the point is to pick up damage that hasn't been accounted for.
Thanks, Kathryn. I think we need to move on. But